Yes, sir. So, dear participants, welcome to the fifth day afternoon session, and the same resource person is G. Venkatesh from NIT Warangal. So he'll be continuing his discussion on RSM with a case study and like what the parameters and the process that we have seen in the morning session. Sir is going to explain in detail with RSM model, and sir is going to demonstrate on his particular case study. So, sir, over to you. Please kindly share your screen, sir. I've given the right, sir.
Yeah, okay. Yeah, yeah.
Sir.
Can you able to see my PPT?
Yes, sir. Yes, sir.
Yeah, just as I would like to play the video which I enabled to play in the PPT. So this is
Okay.
actual original setup of UAFM. So here you can see the function generator, and this is the DC offset, and these are the KC N15 amplifiers. So here you can see this setup is interfaced, uh, and the actuator you can see it is mounted for axial direction vibrations. So here you can see the flexible medium and the fixture. This part we call it as a fixture, and this green part is medium cylinders, and these are the hydraulic cylinders. So before developing this machine, actually we have done some design before fabricating. So you can here you can see the design model. So this is developed using CATIA. I think using SolidWorks it is. So here you can see the actuator fixed, and you can see the vibration of the workpiece radial to the media flow direction. So it is radial to media flow direction. Here you can see this machine is developed for multi-purpose. Say for example, you can see here the gear train. So this gear train can be engaged with the motor, and you can insert the centrifugal rod, etc., and you can do centrifugal force machining. And without engaging this, by using this actuator, etc., you can perform ultrasonic frequency. And by changing the direction of frequency also, we have done some simulation. I would like to show, not simulation, it is basically animation we have done using SolidWorks. So here you can see the vibrations are in axial direction. So this is our semi-solid medium pressurized to and fro from the workpiece, and here you can see the workpiece is in the axial direction, right? The direction of workpiece vibration are in the axial. So in two different cases, we have designed the setup, and same thing we tried to fabricate. You have seen in the original machine setup, right? So like before setting the parameters, we have done simulation also. That video you can see. So how to vibrate is a task actually. We defined a user-defined function for vibrating the workpiece, and here you can see the workpiece is vibrated radially, and the workpiece is also vibrated axially. So like in the simulation, we tried to vibrate the workpiece axially and radially, and we recorded the velocity distribution, pressure distribution, and the temperature. And is there any effect in the amplitude by varying the amplitude? Is there any effect in the frequency, etc.? Those things are recorded, and we have done some amount of simulation. So this design, simulation, and experimental part is mandatory when you are working on experimental. And after that, one more complete chapter, like we focused on experimental procedure and design of experiments. Like you can say, what I want to say is how design of experiment and how important it is for every scholar, for any scholar, in order to of experiments, and in order to play with the numbers by doing optimization, and in order to set the process parameters, etc. So here what I would like to show is, so here we have designed the setup, and we have designed each and every part separately. So here you can see this is a hydraulic cylinder, medium cylinder, fixture, piezo actuator, and this is a cylindrical bush workpiece, and this is a medium which is semi-solid in nature mixed with abrasive particles, and this is the total setup after assembly. So this is a multi-variant setup, like you can perform simple AFM, you can perform UAFM, and you can apply magnetic field, and you can perform magnetic assisted abrasive flow machining, and you can use this motor, and with the help of a gear train which is attached in the fixture, you can perform spiral flow assisted, or you can perform centrifugal force assisted. So like that we planned a multi-variant setup, and we developed at laboratory cost. So it is fabricated at laboratory, in the laboratory, and the cost also is very less comparatively. You cannot compare. I mean, the cost is very less when you compare with the commercial machine. Commercial machines are very costly, but the process is capable for finishing micro to nano level. Right? This is the schematic of the setup we have developed, and this is the original setup. You can see, like after design, the execution is like two hydraulic cylinders are mounted, and using a hydraulic setup unit, and you can see the fixture, and you can see the mounting of the actuator, and the entire setup is built on a lathe machine, right? So this is just a lathe bed. We took one lathe bed. So this is a lathe bed, and on that lathe bed we have mounted all this setup, right? One can install at low cost in your laboratory. So that is my suggestion, right? So once you know how to develop the medium and how to do that fabrication, if you have some small fabrication facilities such as hydraulic unit and mounting, and these mounting plates, and design of this fixture, and development of that medium, so one can do in a laboratory scale. So hardly, apart from the actuator, the total cost of the machine will not go beyond 5 lakhs, 5 to 6 lakhs, right? So but the actuator cost is little higher. So we got from Kinetic Ceramics from USA. So it costs around as 20 lakhs, 20 lakhs, and it is under DST project. So this is how, like, we developed the setup, we designed, and we simulated in order to finalize, right? So this is the actuator setup, and here you can see we tried different. We generally call as these are actuator shafts. So these will interface, this will connect the actuator with respect to the workpiece. So we use different materials. We tried brass, and we tried steel, and we also tried aluminum, and also titanium as well, right? So these shafts are for different material and for different dimensions. There is slightly change in the effect of vibrations, right? Once you check the vibrations with the diode, and with also with the high speed camera, we can cross check what is the vibration applied, etc. So there is some slight variation. So based on that, we choose the best one for radial and axial. So workpiece preparation is done on a laboratory scale. So these are the dimensions we selected. Say for example, the initial RA, the initial roughness of the workpiece is maintained from zero point 0.9 to 1 micron. As I said, it is a super finishing process. The initial array itself 1 micron. So we are planning for further finishing of this workpiece. So these are the dimension, and we went for the fabrication of the workpieces. So these are aluminum 20114 series alloy workpiece for cylindrical bushes, and we also took bevel gears as a workpiece using NX steels. So different medium. As I said, we developed our own economical, eco-friendly media, which is very economical compared to commercial media. So by using different abrasive size, we have mixed the abrasives with the polymer. So we use natural wax polymers, which are honeybee wax mixed with some boron trioxide powder, a little bit, and we added some naphthenic oil and abrasive particles for mixing it. So here you can see different mesh size we have mixed, and we commercialized this media like after applying a patent, we already commercialized and we named it as a natural polymer medium. So these are four combinations, four levels we have tried in the experiment. Yeah. Coming to this part, so your workpiece, whatever I have fixed, this is for cylindrical workpiece. So this cylindrical workpiece is fixed with the shaft vibration, which will act as a coupling, and that coupling is connected to piezo actuator. And we have a circuit here, KCL15 amplifier, DC offset, etc. So we are converting this electrical energy to mechanical energy in form of vibrations. So there is a mechanical change in the workpiece which will vibrate at high frequency, etc. Right. So I also developed another fixture. This is for external surfaces. Say for example, if you observe, this is for cylindrical bush for finishing internal geometry. Whereas when you come to this external workpiece, so our bevel gear will act as an external surface. So for that also some fixture is planned, and we use these formulas for calculating the delta RA. So instead of taking simple RA, we choose delta RA, that is percentage improvement. So initial RA minus final RA divided by initial RA into 100. Here RA is the average roughness, and MR is taken as a material removed. So we have not quantified the rate actually. So we quantified material removed in milligrams, initial weight minus final weight, and the percentage of improvement on MR is also calculated. These are the various setups we have used while conducting the experiment. Like you can see, Taylor-Hobson surface roughness measuring device for measuring RA, and we also use this optical profilometer. So this optical profilometer is whenever you unable to touch the surface, like for example, while measuring the gear, right after finishing, while measuring the gear, it is difficult to land this probe on the gear. So in that cases, we use this optical profilometer for measuring the roughness, and we use this sophisticated weighing machine for measuring the initial weight minus final weight. And we also use the scanning electron microscope for calculate for seeing the microscope before finishing and after finishing. This is a sample cut from the cylindrical geometry, and we use this setup. And coming to this part, yeah, statistical approach for predicting UAFM output. Like this is another important part. Here I have included all the theory about the design of experiment. So here the Y is the objective function for second order. So here you can see the response surface methodology equations are given. It's a high order polynomial equation. So regression analysis is also calculated, and the equations are incorporated here. I mean, all these equations are inbuilt in the software. Once you open the software, and if you perform this ANOVA and regression analysis, here all these equations are inbuilt. But if you want to do self in an Excel sheet, you have to include all these formulas. So formulas in the Excel sheet for calculating, for example, R square, for calculating R square, 1 minus SSC by SST, and similarly mean square. So how do we calculate the mean square? Sum of the square deviation by degree of freedom, F value, mean square of a term divided by mean square for a error term. So like that, like all these are we are getting nowadays ready-made in design of expert software. I would like to just show you how means how these equations are inserted. Like inbuilt software are inserted, but if you want to do on in an Excel sheet, you have to insert in an Excel sheet, and you have to calculate the F value, P value, and R square value, everything manually. Then only you will understand. So the design matrix for radial mode. So while vibrating the radial mode, this is the design matrix I have taken. So I got four factors and four levels. So total 31 experiments using CCD design. So this is the design table for radial mode, and I also got a design table for axial mode. So here, after conducting radial mode, I explored that few parameters were not giving much influence, that I neglected here in the axial mode. And here I am getting 20 experiments with 3 levels. So I reduce the number of experiments when I am conducting in axial mode. This is based on the result of radial mode. And coming to, I also conducted few Taguchi analysis L9 experiments in order to explore the difference between simple AFM and UAFM. Yeah. So just I want to show you just my piece is that design of experiment is one of the important part played in designing my experiments, right? So how I designed etc. Again, I will show you in the slides. I divided my experiment into three phases, right? So first phase, the set of experiments were planned using response surface methodology and finishing of internal surfaces using radial mode in UFM process. Next phase, the set of experiments were planned according to response surface methodology for finishing of internal surfaces using axial mode. So based on the first phase, I realized and I minimized few factors, right? And I minimized few levels, and then I got less number of experiments here in the phase 2. And phase 3 experiments, the set of experiments were planned according to Taguchi array, orthogonal array for finishing of external surfaces using AFM and AFM. This is just for comparison study. If I want to conduct less number of experiments if I want to vary more parameters, then I choose orthogonal array L9. In some cases, in some experiments, majorly when you are working on say for example, if anyone is working on FSW of friction stir welding of steels. So if you are using a costly tool, so costly tool which are used for joining the steel materials. So if the tool is very costly, then probably you cannot do more number of experiments. In that case, you have to minimize the number of experiments by choosing different alternative methods like RSM, Taguchi, and other methods. So depending upon the availability and depending upon the process, we have to choose the suitable one. So based on my literature, based on my experimental conditions, based on my objective and problem, I have differentiated my work into these three phases. Right? Let us discuss the phase 1. So a two-way horizontal UAFM process, which is developed in the laboratory scale, was used in order to conduct the trials. Right. So the design of workpiece tooling and piezo actuator mounting plays an important role here. So the results may vary. The results may vary if you are not properly mounting the actuator and if you are not properly designing the tooling. So here the tricky part is the design of the tool and the mounting of the actuator. So if your actuator is not mounted properly, probably the vibrations were uh, not sent to the workpiece. Means you are not vibrating the workpiece properly at the required frequency. So these two plays an important role. These things you will get to know only if you start doing the experiments, right? So when you apply frequency with and without, and by using proper characterization tool like as I said, high speed camera, like you can record and also you can sense the vibrations applied by using the sensors, and also you can apply the acoustic emissions in order to online monitor the performance, right? So these are the workpiece preparations I have made. So workpiece and media preparations were done as I have shown in my thesis also. So different material workpieces like EN8 aluminum material workpieces are designed for internal and external finishing, and the media is also formulated by mixing four different types of abrasive particle size. So next, chemical composition of EN8 and aluminum 2014 alloy is noted. So what are the measurement and characterization things I have calculated before going to the experiment? So as I already discussed, like delta RA is calculated and MR material removed is calculated, and for for higher the better Taguchi analysis we use this equation, and in RSM the relationship between a response and the process parameters is represented in a higher order polynomial as per the given equation. You can also see plus or minus error. So this plus or minus error can be evaluated once you get the regression equations. So if you enter the regression equation as f of x in the Excel sheet, and if you substitute your xi or A, B, C, D parameters, etc., then you will get the predicted value. And if you have the experimental value, then you can calculate the error percentage with respect to predicted and error. Right now, after a lot of research and pilot study, pilot experimentation study, so the process parameters which are independent in the process in UAFM, in particular in my case, are the applied frequency or the ultrasonic frequency, extrusion pressure, abrasive mesh size, and the processing time. So these four were played an important role while conducting the pilot experimentation and also based on the literature. So here the new parameter introduced is the applied frequency, and in the earlier case this extrusion pressure, abrasive size, processing time, or the number of cycles. Processing time is nothing but the number of cycles. So you can count the number of cycles, or you can actually count the time, machining time or the processing time, by neglecting the idle time. So this also can be evaluated in terms of minutes also. The constant parameters. So in the AFM study, the major constant parameters are which are not having much influence, which are not getting a curvature, etc. So were taken as a constant parameters. So media flow rate, media viscosity, media concentration or abrasive concentration, temperature of the medium, initial surface roughness, and the amplitude. So here these parameters were taken in a range as constant parameter, and the responses are improvement in surface finish and material removal. So these ranges were taken based on the literature and as well as my experimental conditions, and also based on the pilot experimentation study. Next, I have shown you the CCD model of 31 experiments in my thesis chapter. Now, this table shows the results of this 31 experiment trial runs. So here A, B, C, D are my parameters. A is applied frequency, B is extrusion pressure, C is my abrasive size, and D is my processing time. And the results were noted. Results were recorded for each and every experiment. So here my responses are the surface finish improvement and the material removed. So these are recorded. These are recorded for each and every setup. So here, if I identify, in my case, delta RA is the percentage improvement of surface finish. It is always higher the better for me. And also MR, material removed, also higher the better, because in order to have higher finishing rate and higher material removal rate, your objective function should be higher the better, right? In some cases, in the minimization function, for example, if I use RA instead of delta RA, my RA should be lower the better, right? So accordingly, you have to choose at which particular parameter you are getting better, right? In this case, my both functions are higher the better. And if you see, if you observe from the table, so all the initial roughness of the workpieces are maintained in a range of 0.9 to 1. So here at particular run where 15 kilohertz frequency and 7 bars extrusion pressure and 200 mesh size and 7 minutes of processing time, I'm getting 77.34 percentage of improvement of surface finish compared to initial, right? So this percentage of improvement is calculated based on initial RA minus final RA by initial RA into 100. And MR also you can see, this is the maximum MR achieved in that particular case. However, the both are maximum at this particular level. So I highlighted here. I highlighted here. However, from this data, I can also plot the trend curves or the individual effect on the process response, and also the combined effect of the process response. So that is the beauty of RSM. So we can explore the process and the responses, and also the combined effect and the interaction of these processes on the response. A lot of data can be generated with the help of less number of experiments, and a lot of with less number of experiments, lot of data can be generated in by conducting this response surface methodology or using any design of experiment technique. So here this plot shows the predicted versus actual plots in RSM. So on the y-axis you can see the predicted surface finish improvement. On the x-axis you can see actual surface finish improvement. And here you can see the slope line, and the dots refers that the experimental values for the output 1 and this is for the output 2 were very close. The predicted and experimental values have a neat agreement. There is a clear agreement that your prediction based on your regression analysis and the experimental values have a neat coincidence, and they are very close. So that shows that your model is identified, your model is valid, and maybe you have to check further the lack of fit, p value, f value, r square value, adjacent r square value, etc. Right? So coming to figure C here, if you see, so here I try to plot the RA values actually. So instead of percentage delta RA, the RA values were plotted. The blue color shows the initial RA and the red color shows the final RA values, and the percentage difference has been evaluated in the experiments, has been evaluated in the RSM, right? So here you can see these are the trials, up to 31 trials, what is the initial RA maintained and what is the final RA achieved. You can see some up and downs, and some better finishing and some rough finishing, etc., from the trend graph, right? So the regression analysis is also conducted. So it will mainly focus on the relationship between the dependent particles and the independent particles, right? So here I have two responses, surface finish improvement and MRR. So the regression equation has been generated by using all the equation by using the software. So we have developed the regression equation, and R square is calculated and adjusted R square is calculated. So using these regression equations, you can calculate the error with respect to the percentage improvement, with respect to the predicted value and actual value. What you have to do is, so this is the equation. If you read minus 20 MR, for example, if you take MR minus 27.92 minus 0.01 so and so into A plus so and so into B. So you insert this equation in an Excel sheet and give the ABCD values. So ABCD values probably you will get from here. For example, 15, 17, 300, 5. So this is the ABCD value for the run 1. And your result is 65.36, 11.52. This is your experimental result. Just beside that, you add one more column here and write down, insert the equation here, say it as f of x, right? F of x, and another equation f of x dash, right? There are two responses, right? And insert this equation and see the error between the experimental and actual, right? Experimental and regression equation. So based on that, you will find the error, and error should be always minimal. So if you are getting more error, then you have to rethink your design. You have to maybe plan to do some experiments. You have to remove, you have to set your parameter levels, you have to change the parameters level, etc. So always this, after getting this regression equation, one has to check the error with respect to the actual values. Hope you are following, right? After inserting these equations, you just cross check whether you are getting error or not. So the maximum error is I think 1 to 5%. So more than I think 5% or more than 10%, it is not considered. Generally, if you are publishing any paper based on experimental design and design of experiments, RSM, etc., generally the reviewer also may check the error, and also if he is not getting the proper result, then there is a chance of error in the equation. If there is error in the equation, then there is a chance of error in your model. So you have to cross check before validating. Yeah. So coming to finishing through AFM and UFM comparison. So here small data is compared here with zero frequency and by varying frequency for both surface finish and MRR. So here it's a clear understanding that with simple AFM the percentage improvement is less. With the same time, by varying the frequency, the surface finish and material removal will vary. However, here you can observe at 15 kilohertz it is more, and then at 20 kilohertz it started going down. So this is maybe due to at 15 kilohertz it reaches its maximum frequency, and further increase of frequency with the combination of pressure and other parameters, there is a chance of abrasives getting scratch on the workpiece, and therefore result in lower surface finish. So in order to find the optimum parameter in case of applied frequency, the combination of other parameters, you need to know where it goes optimum, and then further it starts deteriorating, right? Whereas in case of material removal, you can see there is no change in the material removal, so it keep on increasing. There is no optimum value found, but however, the material removal rate may increases further if you increase your frequency. Whereas the process is a surface finish process, we are not much worrying about material removed. So we can use up to 20 kilohertz, and you can take the best among this, and you can mainly concentrate on the surface finish of the particular process. Yeah. Coming to radial mode UAFM, when I plot the independent effect or the individual effect response curves from the data, so here you can see the applied frequency and its trend, and the extrusion bar and its trend, and abrasive size and its trend, and also the processing time and its trend, right? So here the applied frequency increases with increase of frequency, the surface finish increases with increase of frequency, so higher the better. So like it's keep on increasing. So here we need to find out an optimum value. Otherwise, if the frequency increases, we observe that there is a chance of scratching, etc., and further deteriorate the surface. So we need to find out the best optimum value in order to get the best surface finish, right? So extrusion pressure also, there is an optimum, there is a curvature you can see. So by increasing the extrusion pressure, there is a you can see keep on increasing delta RA, and further there is drop in the finishing. That may be due to high applied pressure. The abrasives will scratch, and there is more axial force to the abrasive, and it will hit the asperities, and the result is slight deterioration in the surface finish. So here you can see the abrasive mesh size has not shown much result. So it is showing something in a reverse manner, like initially it is showing better, and then it is deteriorating, and then further it is increasing. So the phenomena in abrasive size is basically, if the mesh size is lower, it should show higher, means lower surface finish and higher material removal, right? Whereas it's not following the trend, maybe because of the quality of the abrasive, or maybe because of the abrasives are getting blunt while machining. So that's why this maybe based on this result, in the next experimental set, the abrasive size is neglected, and it kept as constant, and we continued doing the experimental setup. And the other way, in the other side, you can see the processing time. So the processing time keep on increases. You can find the surface finish is also increasing. So, so this is one of the important parameter which plays an important role. Further, the trend curves we already discussed in the morning, like it will show the higher value, medium value, and the saddle value. So here the three types of curves you can see. So this is the saddle point, and here you can see the higher point, and here you can see the lower point kind of results. So here this result shows the combined effect. These are the surface plots achieved for surface finish improvement while working on UAFM. So when applied frequency and extrusion pressure, say this axis, this side extrusion bar, and this is applied frequency, and this is percentage improvement of RA. You can see the three-dimensional parts, three-dimensional data, uh, and the trend curves for the combined effect. As we discussed in the morning, there are three types of curves. Those three types of curves can be noted from your results. Similarly, the effect of material removal is also quantified. So for applied frequency, exclusion pressure, abrasive size, and processing time. So however, here the result is interesting. So if you see the abrasive mesh size, so if the mesh size is less, if the mesh size is less, it means that the particle size is more. So if the mesh size is more, means the particle size is less, right? The particle size is, less. So finer the mesh, higher the mesh actually. It means if you take 2000 mesh, the particle size will be very low. If we take 100 mesh, the particle size will be big. So it is reverse. So here it is clearly observed that the material removed will be high at lower mesh size of the abrasive particle, so at 150. So the other curves are also following the trend. So by increasing the extrusion pressure, you can observe the material removal rate, and by increasing the applied frequency, you can observe the trend of the material removal rate. And similarly, by increasing the processing time, you can clearly observe the trend curve for increasing the MR. So similarly, the 3D plots are also plotted for the combined effect of the parameters on material removal rate. So here also you can see the higher, lower, and saddle point, and this combined effect will shows the interaction plots, will show the interaction of the parameters on the response, and this data will be useful to have a detailing about the experiments, and also will help you for proper prediction of the data, right? So after doing RSM, I suggest always to do the experimental validation, right? So first we have developed a setup, we have done simulation, we have designed the setup, and we have planned the experiments based on phases, right? Why phases are planned means like to cover all the parameters and their ranges, like three levels of means, for example, for axial mode, for radial mode in my case, and for comparison of AFM UAFM. So I cannot do only one set of experiments. So in order to cover all these parameters and ranges, I plan three sets, right? So for every set, experimental validation and simulation proof is required. At least experimental validation, right? This scanning electron microscopy, and also the RA which we are calculating, and MR which we are calculating, will gives you the support to your experimental set. So here this figure shows the scanning electron microscopy of the UAFM samples. So for at different frequencies. So you can see the media flow direction and hitting at an angle theta, and the media flow direction and the abrasive scratches, the deep scratches in certain cases, etc., can be recorded, and based on that you can also produce the finishing of the sample. Means you can measure the finished sample of the result after UFM process, right? So ANOVA, this ANOVA table is very important. Like after doing the regression analysis and after doing the RSM, like after applying the hands-on RSM in the software, etc. This ANOVA is very important. It will know you whether your model is significant, your lack of it is not significant, and also it will let you know your F value and your P value, as we discussed before, like whether it is significant or not significant, and R square, which should be maximum to 1. Closer to 1 is the model is well accepted. So there are some terms and some terminology in order to know whether your model is fit or not. So if your model is not fit, probably if you are getting significant in the lack of fit and not significant in the model, and your p value is not in the range, and if your r value is not in the range and f value is not about the range, then you have to rethink your design. And it states that actually your model is not significant and there is some error in the interaction plots or the combined plot or the choosing the parameter level, etc., or while conducting the experiment, or you need to repeat some experiments based on the error. Each and every experiment is generally planned for three work pieces. Like for example, the first trial, you have to work on three work pieces, and the average of that result of three work pieces will be taken. Then only your data will be validated. The raw data you are maintaining is important nowadays. The papers, the journal papers, they are asking the raw data to put in the appendix, so that they will see whether your data is valid or not. If there is any error in the ANOVA table, etc., then probably they'll look into the raw data. In some case, like they ask to provide some raw data in the appendix, or to provide these ANOVA tables, etc., in the appendix if they are not mentioned in the paper, right? So I validated using RSM. Like I have cross-checked all this lack of fit, F value, P value, etc. And further, I thought I will also use one more model in order to validate my RSM, right? In order to have a better comparison. So I choose fuzzy model, right? So fuzzy model is a hands-on free available in the MATLAB. So if you type fuzzy model, like you will get this fuzzy logic will be applied in order to predict the data. So I have done small case study. I will show you. So A, B, C, D are my four parameters. So ultrasonic frequency or applied frequency, extrusion pressure, abrasive size, and D is my processing time. So I applied fuzzy Mamdani principle, fuzzy logic, and here RA is my response percentage, and MR is my another response. Okay, so the input and output parameters of the fuzzy logic control are shown here. So these ranges 0 to 25, sorry, 0 to 20, and 2 to 22. These ranges, how we have to fix in the fuzzy model are, you have to slightly take lower value and slightly take the upper value of the ranges chosen in RSM, and you have to arrange this lower range, medium range, and high range for your input parameters. Are you getting? For example, my frequency is 0 to 20. I am slightly increasing it. If you observe here, I am taking up to 25, right? 0 means simple AFM, right? So here also you can see my maximum range in exclusion bar is 22, but I am taking here up to 25. Means I am just spreading lower value and upper value in order to choosing the input variables, and I am giving the range for lower, medium, and high for all the four parameters. And the next step is the surface finish improvement. Also I am giving the ranges. Also I am giving the ranges: low level, medium level, and high level. I am naming it as low level, medium level, and high level. I got some idea about in the experimental table that my lowest surface finish achieved is say something 20, or say something 25. So I'm giving little lesser value, and if my highest value is say 77, I'm also giving little higher value than the achieved one. So I'm giving the ranges like this: lower, medium, and higher for both surface finish and MRR. And then this fuzzy simulation model you can create in the MATLAB itself. So this is fuzzy logic controller. So here you will add a lot of rules and rules in the fuzzy model. And here this A, B, C, D are my input variables, and surface finish and MR are my output responses, right? So here I tried one prediction. If you see, three is not my applied frequency. Means I cannot give 3 kilohertz. I have not done in the experiment as well. Five, five also I have not done in the experiment. This is 5 bar extrusion pressure. I have not done. 800 mesh size. So 800 messages I have not purchased and I have not used also. 3 minutes, 3 minutes also I am not right. But I can predict it actually. How I predict it, etc. I will let you know. So these ABCD values you can give within the range or beyond the range, and you can apply the fuzzy logic and you can get the response. So these responses were recorded and you can calculate the error with respect to the regression equation and as well as the experimental result. Yeah, under rules. So these rules are written based on your experimental setup. For example, we know A, B, C, D values, and we also know the data for 31 experiments, and we also know the trend of A with respect to the response, trend of B with respect to response, and trend of C with respect to response, as well as D, right? Once we know the trend of these parameters, how it will act according to the response, then you have to write under rules. Maybe I have written some 100 rules that stating that if A increases, B increases, C increases, D increases, then what happened to surface finish? Either it increases or decreases. That is one rule. And the another rule is, say if A increase, B decrease, A increase, C increase, D decrease, then what happened to surface finish? I will just write a rule. I will write a rule that surface finish will increase. So similarly, if A decrease, B decrease, C decrease, D decrease, I will write MRR will increase. So this data, generally this idea I will get from the 31 experiments based on my experimental knowledge and also based on my literature, right? So like that, you have to take the probability, permutations and combination, trial and error rules, as many as rules you can produce, but that rules should be significant with respect to your experimental data, whatever the experimental values you got. For example, I know the literature. I understand that if A increases, I understand that the applied frequency 15 kilohertz is giving optimum, and more than that is also fine. So if A increases, I know that the surface finish will increases. I will put if A increase, B increase, and C is the abrasive size. I know that lower the mesh size will be better for material removal rate, and higher the mesh size will be better for surface finish. What I put rule, if A increase, B increase, and C increase and D increase, the surface finish will increase, whereas material removal rate will be low, because here I am using C as 400 or 500 or higher mesh size. So like that, you have to plan the set of rules, and if you double click this in the MATLAB, so you can add so many rules as possible, and after that you can freely predict the data, and you have to compare the prediction data like I did. Like if you here can see the percentage of error for test cases based on fuzzy logic simulation model. So here we have done some confirmation experiments. That is also very important. After doing RSM, after doing all ANOVA analysis, regression analysis, etc., you need to perform some confirmation experiments so that your model is much valid, and also you'll have some confidence on your developed regression equations, and you can also find out the error, right? So here you can see I have conducted some 5 confirmation experiments for A, B, C, D values, and these ranges were not used in the experimental table. That is my 31 experiments RSM table, and I have taken 4 parameters and 5 experiments you can see. And this is an experimental value. Like if you have setup and we have workpiece, etc., I can easily conduct experiment. I have done experiments. So here you can see the experimental value, and regression means after inserting the regression equation in the Excel sheet, by varying this ABCD, you will get the regression equation. And in fuzzy, so for example, if you see the fuzzy logic, I have shown you the fuzzy logic controller. So there also, if you enter these particular values, you will get certain data, you will get certain information about your surface finish and MRR, and you calculate now the error, right? So the error for regression, the error for fuzzy, and the error for surface finish, and as well as the error for MRR. It's easy. So if you observe, So here this is my regression. So this regression with respect to experimental, what is the error? And regression fuzzy with respect to experimental, what is the error? For this table is for surface finish, and this table is for MR. So here you can see that in fuzzy logic the error is slightly high because it's based on AND/OR rule. Whereas in the RSM, the error when compared to the first experiment, it is very low compared to compared to regression equation, right? So like this, you can compare the regression analysis or the RSM with respect to fuzzy as well, and you can find out whether your data is valid or not by using the other tools such as fuzzy model, right? So this is how I have conducted few experiments and study on fuzzy model in MATLAB. So it is ready available in MATLAB. One can try using these AND/OR rules. Once after completion of your set of experiments based on AND/OR rules, you can slightly change the logic. So the controller will give you the predicted value, and based on the experimental value, you need to compare the predicted value, and you can generate the error. You can see the error percentage, right? So like that, I have plotted also. Here you can see the neat agreement of clear agreement of surface finish improvement. Three different colors here you can see. Blue is the experimental, red with dotted is fuzzy, and green is the regression. You can see the close agreement between the experimental fuzzy and regression analysis results for confirmation experiments. And if there is if these are not closely agreement, means then, for example, your fuzzy is not giving a close agreement, it means that your rules are not correct and you have to edit the rules or you have to add more rules. Then only you will get. So you need to work on it actually. You need to work on it in order to get the close trend or in order to get the neat agreement with respect to the regression and experimental analysis. Yeah, similarly, I have conducted a response surface methodology for for UAFM in axial mode. As I said, I can't combine this axial mode and radial mode in a single set of experiments. So I separately done the both experiments with the different workpiece material as well. So, but however, based on the first set of experiment, I could know some changes. I could able to identify some changes like abrasive mesh size, etc. I have to constant because at 200 or 150 mesh size, it is going better for it is giving better performance, and the trend for surface finish is not clear when the increasing and decreasing of the mesh size. So this I have minimized, this I have screened based on my phase one, and I took three parameters, say ABC, ultrasonic frequency, exclusion pressure, and processing time, and I have taken only three levels here again. Why? Because I know that at 15 kilowatts itself, the ultrasonic frequency, the finishing rate is high, and further increase after 15, there is slightly decrease or deteriorate in the surface finish. So I modified accordingly, and I have conducted the experiments again. So here you can see the surface finish and material removal rate. So why multi-objective optimization required, I will let you know. In the previous case, if you observe, the percentage improvement of surface finish and MRR are better in one case itself, in one trial itself. But whereas in the second phase of experiments, here you can see for this particular run, trial number 4, so here you can see the surface finish is improvement in surface finish is 76, whereas the material removed is 21. Whereas in the other case, trial number 14, the surface finish is 85 and the material removed is 13. So since it is a surface finish process and you have to give top priority to percentage improvement. However, in the other processes or if you are working on any other process, if for you if both parameters or both responses are important, then you have to go for multi-objective optimization. In that study, you will go for either minimization function or maximization function. and you can get the exact optimum values. You can get the ABC optimum for maximization of surface finish and maximization of MRR. So that particular set you will not get from the RSM, right? So if you observe, you will get the trend curve, you will get the individual effect, you will get the combined effect, you will get lot of data using RSM, but you will not, you probably may not get the condition where you will get both, you will get your responses will satisfy at both, right? At both means, in my case, maximum surface finish and maximum material removal. And that particular condition, for that particular condition, you are supposed to do some multi-objective optimization. Whereas another case also, using the regression analysis, probably you can vary these numbers A, B, C, and you can perform the regression equation, and you can get some predicted value. However, that prediction is also should be compared with some optimization technique in order to validate. So similarly, in this case also, like I have done regression analysis. So I have done ANOVA analysis. You might have already gone through about ANOVA and regression in your previous sessions as well. So I have seen the conditions: lack of fit, non-significant, not significant, and the model significant. I have checked my p values, f values, and also I have checked r square values, adjacent r square. Everything I have checked, and once everything is clear, then I understand that the model is fitting, and it is having better correlation with respect to my experimental. So these are the trend curves. Again, here you can see for surface finish improvement and material removal, and material removal, and next some experimental results for analyzing this surface morphology, etc. Here you can see. So these are some experimental proofs for different conditions were plotted. So these are taken from the optical profilometer. So before and after RA finish, you can see here the pre-finished RA 1.8 micron. So this is a case of gear actually. So for cylindrical bush, we took zero point 0.9 to 1. This is the case of gear. So we got up to zero point 0.2 micrometer after UFM finished. And these are few scanning electron microscopic images where you can see the trend of abrasive particle hitting at an angle theta, and also the abrasive deep scratches, and also the finished surface. Even though the surface looks deteriorate, here you can see that the zooming, the magnification is around 500x. The 500 times it is zoom, right? If you see with the naked eye, you will find some mirror image. But if you zoom it, probably you will look into the machining layouts, machining flaws, etc. Means what are the machining directions, the abrasive direction, etc., and the deep scratch, etc. Probably you will look. Yeah. Yeah, so in order to find out the multi-objective function, and also in order to find out the best solution, so I also performed Jaya algorithm for UAFM study in order to find out the multi-objective. As I said, so for two responses, if I have two responses, for two responses, like what are the parameters required? What are the parameters and their levels required in order to find out the best solution? So Jaya algorithm is proposed by Professor Rao in 2011 for solving both unconstrained and constrained problems. Jaya algorithm is applied with the help of it is it means there is already coding available, MATLAB coding available on internet. So using that MATLAB coding, you can use your regression equations and ranges for your parameters A, B, C, D, and you can vary them. You can vary them in the coding, and you can run the code, and you can find out the like best and worst values. So let us see the chart. That this chart is clear in the next slide. Yeah. So first, in Jaya algorithm, start define population size. Right. The population size is the number of experiments you are going to conduct, the number of variables, and sorry, and the number of and the termination criteria, right? Population size, number of variables, and the termination criteria. You can see the flowchart. Find f of x. F of x is here the objective function. It means I have two objective functions, right? Delta RA and MRR. So delta RA is my f of x. Find f of x value for each population. Population is actually the ABCD values, means the my input variables. So these are randomly generated. Here we are not using the actual what we have used. So these are randomly generated in the setup in the J algorithm when you are performing optimization. And note down that f of x value and worst f of x value. In my case, higher maximum surface finish is the best value and the worst is lower surface finish. So I'll just note, I'll make a note when I'm doing manually. Next step is for maximization, higher f of x value is f of x best. Okay, for lower f of x value is worst. What it means is, if your objective is maximization, if your objective function is maximization, then higher is the better, right? And the lower is worst. And if your objective is minimization, lower is the better and higher is the better. For example, as I said, I'm taking percentage improvement of RA, so maximum is better in my case. But in some cases in AFM, some people are working on RA values, so lower the better. For them, minimization. So the flowchart looks like this. Like you have to note down the best value and the worst value, and then you will run the code. So this is the code actually. So what this code says is xi new, means in order to generate a new value, so you need to know the xi old. The xi old value plus r1. R1 is the random value, mod of xi best minus mod of xi old minus r2 mod of xi worst minus xi old. So this is the code actually. Based on this code only, your entire optimization will run. What Professor Rao tried here is he he reduced, means he reduced the worst results from the best, means he's taking the best among the worst results, means he's getting close to the best and moving far away this worst values. Means for every solution there is a best result and worst result, right? He's taking this equation, helps him to take the best result and lose the worst result and proceed. So that's what this logic works. So the next step here you can see, find f of x, means objective function we will find f of x values for the new variables. And if f of x new is greater than f of x, okay, if yes, then replace the earlier solution. If no, keep the early solution. It means that, so once if you run one generation, one iteration, in that iteration, whatever the new, if the new is better, you will take the new. Or if the old one is better, you will take the old one and keep proceeding like that. Like, is the termination criteria fulfilled? So if the termination criteria is fulfilled, if no, then you will go to the loop again, and if yes, you will print the optimum solution. I would like to show one Excel sheet on this Jaya algorithm, so for easy understanding. So yeah, so here if you see the initial population, I have taken say 25. So I have taken 25 runs. So A, B, C, D are my parameters. So A is applied frequency, B is my extrusion pressure, C is my abrasive size, and D is my processing time, right? And F is my objective function. So this F regression equation is inserted in the coding, so that is done. And these are randomly generated A, B, C, D, and this is my f of x generated from the coding after as per the you can, as per the coding and as well as per the technique of this J algorithm, this f of x is generated. Now mine is lower the better I'm taking, because here in this particular one I'm taking RA values, right? I'm not taking delta RA. So my function is minimization, right? So I found the best solution as 0.013 is my best, right? And the worst solution is 0.7. So maximum is worst in my case and lower is best. So second iteration, so if you see, so worst is 0.63. What you have to observe is, so if you continue with that logic in the J algorithm, your worst solution also will slightly reduce in the next step. And see, this is our best 0.013, and here in this case the best is 0.011. So your best is improving. What the logic says is, if your best is not improving, then replace with the already existing best and continue, right? So you are by applying this logic, your worst solution also will slightly come down. So for example 0.637, so here also it is 0.637, means it is taking the same value. It means that in this particular iteration you got more worst value, but you are replacing with the existing worst value. Similarly here, so like that, if you keep on run the simulation for the number of iterations, etc., then at some particular point you will find some convergence in the result, and finally it will gives you the solution optimum values, and your values will repeat. That I will show you here. So for example, here you can see, once your result converge, then your parameters levels will increase and your response will continue. So here in this case, this is for MR. So higher the better, mine is higher the better. And here you can see the best solution is 19.11 and the mean is 18.98. Worst solution is 17.33. It means that in the first step your worst solution may be different, but at the final stage your worst solution is also improving according to your objective function. So like that you can run the objective function optimization in J algorithm. That code is available online. One can try by varying your parameters, ranges, etc. Once after running, you will find at some particular point the converse results, and based on that converse result, you will find out the best and worst. So if you take a multi-objective, so how multi-objective is taken, then we know the regression equation for surface finish, and also know the regression equation for MRR, right? MR. So these two equations are inserted with the help of positive and negative symbol based on your minimization and maximization function. These two are inserted in the code, and we try to get a optimum solution for multi-objective type function. Say here this f of x is optimum, and for this particular 20 kilowatts, 2 extrusion frequency, 350 mesh size, and 8 processing time. So like that you can actually run the code and get the best solution and worst solution, and you can improve your worst solution, and finally you can find out the best among the worst, and you can keep continuing. And also we tried by varying the weights. For example, in multi-objective function, so if you are not giving weights, means it is zero point 0.5 for surface finish and 0.5 for MRR if you are not giving any weights. But since mine is a surface finish process, I will give more weight to the surface finish. That is my first objective function. It means I will multiply the regression equation into zero point 0.6 into surface finish equation minus zero point 0.4 into MRR. So I will vary the weights, and I will see and I will see the objective function. So what is f of x for my surface finish and MRR, and similarly I will vary the weights up to zero point 0.2 to zero point 0.5 here and zero point 0.8 to 0.5. So by varying the weights, if you generate the data, you will get an idea that by varying surface improvement, what is your f of x, by varying the MRR, what is your f of x. Why we are doing here means, since mine is a surface finish process, my top priority is surface finish. So here the best solution among this is 0.24, because the lower the better is my surface finish. I am using RA values here, and the best solution among here is 16. So we got up to for 0.5, 0.5 means for giving equal priority to both the equations, we got a optimum solution. In certain cases, it may vary. In certain cases, it may be vary, like 0.6 and 0.4, etc. It may vary. So like that, you can have a study on optimization, and you can compare the data with regression and as well as the fuzzy logic. So similarly, nowadays, recently, that abrasive flow machining is very difficult to install in our laboratory because we require that acoustic and we require that actuator, etc. What we have done is we slowly started MAF. So MAF means magnetic abrasive finishing. It can be defined as a finishing process which uses a flexible magnetic brush. It is composed of magnetic particles for finishing. Okay, this magnetic abrasive process uses the magnetic abrasive flexible brush, and it can be easily installed. Basically, if you have a milling machine in your laboratory, you can simply install this. I will tell you the important parts and how to install it. So just watch this video, you will understand. Yeah. So here you can see this is the electromagnet. So this is the electromagnet unit which we have done winding, and this electromagnetic unit is connected to a dimmer start, and we have a power supply. And here we have a electromagnet, and here bottom we have a workpiece which is a magnetic material, and in between we are maintaining some gap, and we are pouring the abrasive particles, loose abrasive particles, which are slightly powder kind of abrasive particles, and it forms an abrasive brush. So once you apply the magnetic field, so these abrasive particles are mixed with the magnetic particles, so it forms an abrasive brush, and this abrasive brush will do the finishing. Actually, will do the finishing, and this finishing will be much better than the grinding. So we can say it's kind of a buffing process. So we can do finish by using this magnetic abrasive particles. Even though your workpiece is concave, then also you can finish. Why? Because the tool here is not directly in contact with the workpiece. In between there is a gap, and in that gap we are generated that magnetic brush. So here you can see this magnetic brush, and due to the magnetic field, these abrasive particles you can see how they are formed as a brush, etc. So this is also a super finishing process. So here the important parameters are magnetic flux density. So magnetic flux density, speed of the electromagnet, and the voltage applied, and the percentage of abrasives. So here for initial, like we don't have magnetic flux meter, so we do not vary the magnetic flux meter. So with the whatever the resources we have, so we have checked, and we calculated the magnetic flux, and also we varied this percentage of abrasive, speed of electromagnet, and voltage, and we could able to have do only few experiments because due to lack of experimental conditions and as well as other things. So the thing is, like, after doing these experiments and doing this analysis of variance and other things, you can always have a scope to do optimization. So again, we have conducted optimization using genetic algorithm and J algorithm, and we found the error, and also we found the actual and predicted value. We also got the regression equation. That's what, like that we started doing the experiments nowadays on genetic algorithm, and recently we published one paper in part C, IMECI part C, which is on machining of magnetic and non-magnetic materials using magnetic abrasive finishing. So in that I have included this DOE part, and as well as the optimization part, and also the experimental part, etc. So this way, like, once you understand the process, and once you know the parameters and their levels and their ranges, and maybe based on the experimental conditions and based on many other things, you can probably start working on this DOE and optimization things. And I would like to conclude my experimental setup, like based on the principles, and based on the experimental axial and radial, what is maximum, what is higher, etc. I have given here. Like for the most significant factor in UFM axial is applied frequency and extrusion pressure. Why? Because I got better surface finish in that particular thing. And whereas while working on radial, my surface finish increases with increase of applied frequency. And when working axial, like I would like to conclude them. Right? Material removal increases with the increase in applied frequency with extrusion pressure. So abrasive hits the target surface at an angle theta in my case because I am vibrating the workpiece. And what is the future scope is possible is like one can introduce the acoustic emission technology for this UAFM, and one can do the multi-objective function when radial and axial both are involved while machining. So when two actuators are used, one is arranged in radial, one is arranged in axial, and one can perform when actuator is inserted and also the drill bit is inserted in a UAFM. One can study the effect and one can optimize it, one can design the parameters for it, one can introduce the new parameters in case of axial mode for different materials. One can try working on composite materials. One can try working on additive manufactured materials. So like that, there is a lot of scope. If you take any area, your area may be FSW, EDM or ECDM, like there is always a scope to have a future to work on the, like, you don't believe still people are working on simple grinding, right? Still some people from means you can say from IIT Madras, some people are working on simple grinding process, right? The process is not important, the way you understand and the way you explore them and the way you present to the society and also to the world is important, right? Whether it is useful, whether it is useful for the industries or whether it is useful for the research scope. So that is what important. So my suggestion to all the scholars is, so whatever the area may be, you have to explore the future scope, and there is always a scope to have a new problem, innovative problem in your case. So similarly, I would like to conclude the MAF process. The optimization of MAF has been computed using the newly proposed J algorithm. So the result obtained by J algorithm are higher compared to Jaya. So genetic algorithm is giving higher better than Jaya, but number of iterations were less in J algorithm. That's what we observed. So this is what about my recent and few PhD studies. So some of the studies I have included. So I will share you some mail related to this links of the papers or any PDF. Someone asked a PDF, so that I will be sharing.
Okay, sir. Thank you, sir. If anyone, any of the participants need any discussion or any clarification, please kindly unmute and you can discuss.
Hello, sir.
Sir. Yes, sir, you're audible.
Sir, kindly, if possible, kindly share that MATLAB program for fuzzy logic and J algorithm, sir, if possible.
The J algorithm is openly kept in the internet, but I will give the link. Okay, actually, the author idea is he shared all the codes and he wants people to work on it and he wants citations. So that idea is clear. So we also published one or two papers, and the optimization techniques were very useful. That the techniques are very useful, and his workshop is also every time he will conduct. I think many people know. Professor R.V. Rao from
SVNA.
NIT Surat, yeah.
Yes,
So,
sir, SVNA, please.
yeah, one can try, it is free of cost, only, no problem. So you can try, I will share, if you want, I will share the link.
Okay, sir, thank you very
Fuzzy
much.
logic is mostly based on the your literature knowledge, how you are writing the rules is important. So otherwise your prediction may slightly increase the error.
Yes, sir.
Okay, sir, thank you very much, sir, thank you.
Any other? Okay. So, sir, actually, like what you have said on the usage of MATLAB, and then when we are combining gray, and then you are used several algorithms, and you were able to conclude with some justification, sir. So, when it comes to validating these things, sir, how was the result? Uh, and you have already shown that
Yeah,
the
some
algorithm was
experiments were
showing.
validated and we cross-checked with the experimental regression and other things.
Yes, sir. So all the results were encouraging, sir.
No, no, actually we validated for RSM, regression and fuzzy. But J algorithm and genetic algorithm, genetic was showing better.
Okay.
This Jaya is not there in the MATLAB, but we have
Yeah.
code. But
Uh,
genetic and all we are ready to use genetic and other things. But we found Jaya is giving for less number of iterations, less time. And for validation purpose, actually, means if we have set up, probably we can try for
okay.
multi-objective type. But right now we don't have set up. So, but MAF we have tried. UMAF we did not try. Like ultrasonic we did not try. That J algorithm multi-objective.
So this was even performed on the newly developed medium also, sir. The
Yeah,
media which was okay.
the whatever the media we developed after MTech, we are using that medium only. We
Okay.
compared the simple AFM. When we are working on simple AFM, then we compared with the UAFM and simple AFM. But the medium
Okay.
we used is the developed one. But while
Okay.
developing the medium, that results have not shown my MTech results. There we have again a case study. There I compared the existing medium with the characterization and we conducted again response surface methodology for finding the better medium, preferential medium for AFM.
Okay. Any other doubts, participants? You can unmute and you may ask. Okay. Okay, sir. Thank you very much. It comes to the end of this session, and thank you very much, sir. First of all, for accepting the invitation and then giving us a complete package on the AFM, ultrasonic assisted AFM, and then usage with the process parameters. So those who are actually going to take up finishing in fact to that matter, any manufacturing process is concerned, you have given us clear picture about how the process selection has to be done and the care that we need to take, and then finally when we arrive at these are the controllable factors and this is where we need to emphasize, then from that point onwards till the main factors, interactions, and the objective function, then selection of various different types of algorithms, usage of MATLAB, and then fuzzy logic, and the newly evolutionary algorithms. And like you have rightly pointed out, like Rao, SVN, yeah, SVNIT, yeah, Surat, he is a pioneer in this area of evolutionary algorithms, and he is conducting workshops every year, in fact. And that is a very good place. Those who are looking for optimization techniques and they want to enter into optimization area, I think that his workshop will work a lot. And his Springer book is also very fantastically written, especially for the manufacturing persons like us. So yes, sir. Right. This is what actually is useful for the other participants also, those who are looking in this direction. Thank you very much, sir. It was a very good session, and I enjoyed a lot going through all these in detail discussion on the ultra abrasive flow machining, ultrasonic assisted abrasive flow machining, optimization techniques, and all. Thank you very much, sir. Thank you for the sharing us all the hard work and the presentation of your research thesis. Thank you, sir. As requested, if you can share those PPTs, I'll
Yes,
try
I
to
will
communicate.
mail you the link,
Sure, sir.
whatever available, and the
Sure,
papers
sir.
related to that.
Sure,
Yeah,
sir.
and
I'll,
thank you, Dr. Varun, for
thank you, sir.
inviting me, and thanks for your successful workshop, and all the best to all the participants. I would like to give my best wishes to the participants.
Thank you, sir. It was a very lengthy session. I hope you have given the best. So I think the participants are all taking something away from this discussion, sir. Thank you, sir. So I'll end the session, and for the participants, I'll share the feedback link through the WhatsApp group. So you can fill that feedback link through the WhatsApp group. And tomorrow we are going to have again at the 10 o'clock, and the speaker is Dr. N. Venkaya. He is from IIT, Tirupati. So Associate Professor Mechanical Engineering, IIT Tirupati. He is going to give on advanced areas of metrology and design of experiments. Thank you, sir. I'll log off.
Yeah.
Thank you.